Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be taking our knowledge of the three principal quantum numbers and applying it to real atomic systems. So it is worth noting that our principal quantum numbers were used to originally describe a set of orbitals for a hydrogenic atom, so any atoms involving a single electron. However, it turns out they're a fairly robust descriptor of how electrons work even around multi-electronic systems. So when we're going to be talking about electronic location, we're mostly going to be using the orbitals I talk about today. Now, we have our three principal numbers, n, which helps denote energy and size, L, which helps denote shape, and M sub L, which denotes direction. So most of the time, we're going to break apart our descriptions of orbitals based on which subshell they occupy. So again, what L they have, because again, this dominates shape and shape will dominate a lot of our behavior. And one of the things worth noting is that when we're going to be describing orbitals today, I'm either going to show these as a mathematical function, either denoting the wave function or the probability, or if I show a pictorial map, really what this figure is showing is where 90% of the electrons are located. So in this case, 90% of the electrons are located in this sphere for the 1s electron, or along this dumbbell shape for a p orbital, or for a d orbital, they're located along this kind of ballooned out X shape. So let's go ahead and start by talking about the simplest of our orbitals. That's going to be our S shell, or S subshell, which has an L equals 0. And as I've talked about previously, one of the big things when L equals 0 is we have an equal probability density in all directions. Thus, the reason it's represented in a sphere. If you apply this to an X and Y plane, what you see is an equal probability density, or a probability density that peaks near the center and then trails off equally in all directions. You can also see this in a contour map where we have high density near the nucleus, because why wouldn't the electron want to be there? And it tears off as we go further out. And again, this helps describe the 1s subshell. And one of the big reasons why we have this even distribution is the electron has no directional movement. It's just randomly wandering around the nucleus, which as a result means it spends most of its time near it and a little bit of time further away. So good way to think about this is that I've got a lazy Sunday afternoon and I'm going to probably stay near the phone, my computer, or a good taco stand. Whatever it is, I'm going to spend most of my time there, but I'll wander away from time to time. But with no reason to be in any one direction or another. And that's really what we see here. And it is worth noting that as the n increases, we're going to see slightly different shapes, as we're going to have an increasing number of what we call radial nodes. And really what the radial nodes mean is that I'm going to hit this 0 point periodically in between. So if looking at the probability distribution, if n equals 1, L equals 0, the area near the nucleus is really small, so I'll occasionally be there. But because I've got more and more space further out, I'm more likely to be found somewhere at an intermediate distance. And as the distance trails out, I'm going to be less and less likely to be found. As n equals 1 or n equals 2, what happens is that I'm going to have a single radial node. As I'm going to have a slight probability density here, a bigger one later on, but again, trailing down to less likely to be found further out. As n equals 3, I'll have 2 radial nodes. And n equals 4, I'll have 3 radial nodes. And we can also see this in a more three-dimensional representation. 1s, equally likely. 2s, we have the probability distribution broken up into 2 spheres. And the same thing when we go to a 3s, but now in 3 spheres. And you can again continue this forward. So for a s orbital, the number of radial nodes will be n minus 1. However, things get a little bit more messy when we have an L of 1. So it is worth this generating what we call our p orbitals. It is worth noting that p orbitals can only happen if n is 2 or greater. And the reason why is because, remember, L can't have a value greater than n minus 1. So n minus 1, if n is 2, minus 1 means we can now occupy our first subshell. And our p orbitals are essentially going to be elongated along one axis. And so this gives us this kind of dumbbell shape where we have high probability density along a given axis, but a little bit further out. So a good way to think about this is I've got a kid who can't stop running, but really wants to keep stopping by for a candy bar here in the middle. So it'll run this way and then come back and then back and forth. So it's spending some time running along this axis and occasionally wanting to hang out by the nucleus, but it gets bullied every time it's there because it can't stop moving. And that's really what we see here. Now, one of the important features is that because L is equal to 1, we have 3 possible M sub L values: -1, 0, or 1. And what these essentially reference is that the orbital can point in 3 directions. So we typically point this along an x-axis, a y-axis, or a z-axis. And then we have a plane where the electron can't be located, essentially along the other 2 axes. So if I have a pz orbital, it means we'll never find the electron along the xy plane. If I have an electron in the py orbital, I'll never find the electron in the xz plane, and so on and so forth. So as n and one of the important things is that as n increases, what we're going to find is kind of a nested set of probability distributions, kind of like we had for the L orbital. Where what I'll have, or for the s orbital, what I'll have is that we'll have a little p orbital here, and then we'll have a single radial node, and then we'll have a bigger p orbital further out when we get to the 3pz orbital. And you can see this in the radial distribution. The electron is likely to be located at is most likely to be located at an intermediate distance when we have the L equals 1, or with n equals 2. However, when the n equals 3, we now have 1 radial node. Now, this is a little bit odd because the number of radial nodes is going to be different than for the s orbital. And there's actually a fairly simple formula that we can use to depict the number of radial nodes. The number of radial nodes will be n minus L minus 1. So for n equals 2, I've got 1 angular node, and that's it. N equals 3, I have 2 nodes overall, because total number of nodes will be n minus 1. One of them will be angular, and one of them will be radial. So it is a good way to kind of generally get an idea of the shape of our orbitals. With, again, most of the probability density likely at the higher peak rather than the near one, simply because there's more of the orbital out there in this further out distance. Now let's go ahead and take a look at L equals 2. This generates what we call a d orbital. And similarly, this can only occur when n is greater than or equal to 3. So the first set of d orbitals is going to be our 3d orbitals. They have, in this case, density is going to be spread out in 2 directions. So we often point these along in between our various axes. Essentially, a good way to think about it is to make way for the p orbitals. However, we do have 2 additional orbitals that can be pointed either along the x-axis and y-axis or along the z-axis. And this gives us 5 possible orbitals with an M sub L of -2, -1, 0, 1, and 2. Again, because M sub L can go in between -L and L. And this corresponds to our 5 major directions. The easy ones to remember are XY, YZ, and XZ. So again, splitting the various axes. We have the Z squared and the X squared minus Y squared, essentially picking up the extra density of where these 3 aren't pointed. And you'll note that when we take a look at the probability density of these d orbitals, they look a little bit like a 2-dimensional particle in a box, where the particle is located somewhere along a plane of density, with essentially an n of 2, because I've got 2 angular nodes. Because remember, n equals 3, when n equals 3, I'll have n minus 1 nodes, or 2 nodes, all of them angular. But what happens when n is greater than 3? So as n goes to n equals 4, I generate a now radial node in addition to the angular nodes. So again, just like a p orbital, a good way to think about this is I've got a nested little d orbital with a little bit of density inside my bigger d orbital. So this allows us to try and identify what our major quantum numbers and thus orbitals are simply from a pictorial representation. Now, I want to go ahead and take a little bit of a look out and kind of compare the size of our orbitals, because size is really going to dictate energy. Because remember, electrons like to spend time close to the nucleus. So when talking about size, we've got 2 major factors. The first we've already brought up, and this is going to be n. So as n increases, what happens is the electrons are going to spend more time further and further out. So for n equals 1, we only have the 1s orbital. It's sitting real close in. When n equals 2, our major peak density is a little further out, and then much further out when we go to the n equals 3. However, one of the things that is worth noting is that as we go out, we generate these radial nodes. You can see it with the 2s orbital, where I have this slight peak of density close into the electron nucleus. So while most of the time I'm spending further out from the nucleus, as n increases, there will always be a little bit of density that says, I don't want to let the nucleus go. And that's the important feature of those radial nodes. As I get more radial nodes, I have more little bits that I leave close to the nucleus because they just don't want to let it go. However, this also brings us to the other major control on size, which is going to be L, or our angular momentum. Because remember, as L increases, the electron has more of that angular momentum. It's moving faster. And because it's moving faster, it means it has more kinetic energy, which means to offset this unfavorable kinetic energy, it has to have also a higher favorable potential energy. So the faster the electron is, the more time it's going to spend close to the nucleus. So a good way to think about this is s orbitals kind of go wherever they can, so they're able to sit a little bit further out. The p orbitals and the d orbitals get a little bit more crowded, but they're closer in. So a good way to kind of think about this is if you're at a concert. You can either find a nice easy seat, or you can find a really crappy aisle seat, which isn't a favorable position, but may get you a little bit closer for the same energy. And this is really kind of what we see here. So next time, we're going to be digging a little bit more into what happens to these to the energy of each of these orbitals and their occupation when we have more than one electron present at a time. Till then, take care.